Yeah, so I'm going to be talking about working with bytes, binary serialization, and Elm. Sort of what makes sense here, what doesn't. So this is, I think, a story that starts with this document written by Evan. It's called A Vision for Data Interchange in Elm, and it sort of looks at JSON and how it maybe isn't well suited for Elm in the long run, and some alternatives that we could maybe use. We couldn't at the time really do anything with that, though, because JSON was just baked into all the parts of Elm, mainly in the HTTP library. But then in late 2018, Elm Bytes was published, which for the first time allows us to use binary serialization to send data between the server and the client. And also, we can now decode binary file types that we couldn't really work with before. That is stuff like PNGs or zips or MP3s, etc. Basically all the file types except plain text. So the core idea, of binary serialization is the sacrifice of readability of our messages for an increase in compactness, so sending less data or storing less data, and also speed. So part of that speed benefit is having less data to process, but also we can typically parse certain kinds of data faster when they're binary encoded rather than parsing them from a string. So to get everyone on the same page, a bit is a 0 or a 1, a byte is 8 consecutive bits, and computers already use this representation, mainly because it makes hardware simpler. Like you have just 2 power levels to deal with. The power is on or the power is off. And so all the values that we work with in our programming languages have a binary representation. And so the simplest one is for non-negative integer numbers. So if we want to convert a number like 6 to its binary representation, we look at the powers of 2 that it uses. So in this case, it uses the second power, 4, and the first power, 2, but not the 0th power, and therefore its binary representation is 110. And this already has the characteristics that we want, given that the hardware works the way it does. So it's already more compact than storing the digits. If we store a number like 2019 as its 4 digits, then that's going to take 1 byte per character. So it's going to take 4 bytes in total. If we use its binary representation, it's only going to use 11 bits, which we have to round up to 2 whole bytes, but that's still a 50% reduction. And also because we store it in the format that the computer expects, it's much quicker to load. We don't have to do any processing there. With that out of the way, we can have a look at the API of the Elm Bytes package. And really what I want you to take away from this is that it looks exactly like a JSON decoder if you squint a little bit, especially if you use the decode pipelines library. So a couple of the names are different, but the main idea is the same. In particular, the Elm Bytes package has a sequence type. It's called Bytes, and it's really a sequence of byte values. And this is a type that we encode to and decode from. So this is similar to JSON, which encodes and decodes with a string type, which is really a sequence of characters. Then we have concepts of a decoder and an encoder. So a decoder is familiar from JSON. An encoder, we know they're under a different name. It's called the JSON.value type. But it's really the same idea. And then we can encode and decode some primitives. Those are mostly number types of a specific size in bits. So unsigned int 8 is the simplest one. It just encodes a raw byte. And also a string. So a string is a built-in. There's a certain mapping between characters and bytes that handles all your emoji and other Unicode characters. And this is just present as a primitive. Finally, the signature of decode is interesting. So it takes a sequence of bytes and a decoder of A, and it produces maybe an A, which means that when it fails, when the decoder fails, and decoders can fail when they sort of try to consume more input than you have given them, so they've sort of run past the end. When that happens, you get no error message. You only know it failed. You don't know why, you don't know where, or where the error is. So debugging these decoders is pretty tricky. It's not a fun experience. More so because you can't read the messages anymore because they're all scrambled, they're all bytes. So it's very hard to pinpoint where the actual error is. So with that foundation, we can look at why might this be helpful in practice. So the first thing I want to look at is sending data between a server and a client in sort of a web app kind of scenario. Why would bytes be better than JSON here? Well, the main insight is that JSON sends along a lot of structure with its data. So if you look at this example, the actual data is only 7 characters. It's foo spam. But the whole message is a lot larger than that because it sends along, like, this is actually an object. It has these keys. So this is normally very useful when we're working with data that we're maybe not very familiar with. We can just look at the data. Also, when we're debugging decoders, we can look at it and we can immediately sort of see this is how we should decode this data. But if all we care about is getting data from A to B just as quickly and efficiently as possible, this is quite wasteful. More so when we often send the same sort of structure with slightly different data. So what we can do is try to sort of extract this structure into a table that looks a little bit like this one. So what this does is it lists all the fields that must occur in the message, and it fixes the order they will occur in. And also for each field, the size in bytes and the type of the field. Now you can see that we have some extra fields in this case, the title length and the subject length. And this is because we are using some variable-sized data structures, so like stuff like strings and lists. We don't statically know how long they're going to be, so we can't put the size exactly into the table. But we can't just send foo spam, because the decoder then can't know where the first string stops and the second one begins. And we can't easily put in a delimiter like a comma, because it would be indistinguishable from the data around it, because it's all just byte values. So a common and easy solution for this problem is to first put in an extra field for the size, just as an integer, and then after that, the variable bytes. And then the decoder can handle this. So let's try that out. This is an API call or like response taken from the Flickr API. And the main thing I want you to notice here is that most of its fields are strings. So most of the data will actually be string data. And so I wrote an encoder and a decoder, both for JSON and for bytes, and ran some tests. And I get to a 17% reduction in this case, which is not 0, but it's also not like the 50% that we saw for even a simple integer. Then I also did some benchmarks, and it turns out that bytes is actually slower in this case. It's still 130,000 runs per second, so it's probably fine. But it really goes to show that the built-in JSON decoder is just very fast. So even when we give it its worst nightmare, which is just an array of floating point numbers, and we make that array like 100 elements long, it's still almost twice as fast. It's only when we give it substantially more data that bytes comes out on top. So this is in the case of 1,000 floats. So what I take away from this is that the compaction and the speed benefits that you might get really depend very heavily on the specifics of your data. Do you have a lot of fields, or do you have only a couple? Is your data mostly strings, or is it mostly integers or numbers? Then, even if you think sort of the improvements make sense, you have to also consider the maintenance cost of this kind of decoder. As I mentioned, when bugs creep in, as they inevitably will, debugging these decoders is not fun. So we also have these things like schema formats, like protobuf, and they have benefits of their own, like they support union types better, and you can sort of version your API with them, but they still run into the same issues here that like they're not built in, so they're never going to be as fast on small pieces of data as the built-in JSON decoder. And they also can squeeze a string more compactly than JSON can, because it's just, there's nothing you can do there except compress it, which already happens. Okay, so the second thing I want to look at is a bit more technical, and it's decoding sort of binary files, which I really think opens up a lot of new possibilities. And specifically, what I want to look at is base64. So this is a binary to text conversion method. It takes a bunch of bytes and it produces a bunch of characters. And we use this on the front end to inline small files in style sheets and for creating images. So in pure Elm. So we can create images in sort of a simple bitmap format, then convert those into bytes, which is like the spec defines how you should do that. And then we can convert those bytes into base64 characters, put them in a data URI like this, and we can hand that off either to the browser or even to WebGL, so they can load the data and turn that into pixels on the screen. So this is a nice thing to have, and it's something we can now do easily. So how does that work? Well, this is really base 64 is a 64-digit number system. So we normally have a 10-digit number system. We're also kind of familiar with the binary 2-digit number system. And here they just pick 64 distinct digits to use. And why is that faster? Well, if you look at something like 10 there, which has index 10, which has the letter K, capital K, then writing out the index takes 2 characters, while writing out the K only takes 1 character. So that's why it's faster and or more compact, and it's almost going to be like a 50% reduction. So what I like to look at this in a bit more detail, what I want to look at is sort of the opposite problem. We have some characters, some base 64 characters, and want to turn them back into bytes. So a question that you need to answer here is how much storage do I need to represent 1 character? And in this case, because we have 64 distinct possibilities for each character, it turns out we need 6 bits, which is because 2 to the power of 6 is exactly 64, which is one of the reasons that 64 is a good number of digits to choose. So ideally, we only want to spend 6 bits for each character. But the API only allows us to write whole bytes, or multiples. So we can write 8 bits, or 16 bits, or 32, but not only 6. So we have a bit of a problem there. And we don't want to waste those 2 bits per character, because that's not what we're about. We want ultimate efficiency. So the solution here is actually not that hard. We can use 3 bytes, which means 24 bits, to store 4 characters. And then how that works from there is you take your characters, you look up what their index is in the table, and then you interpret that index as sort of its binary representation. And that's just to illustrate how this works. So now we have 4 6-bit patterns, and we want to turn that into one 24-bit pattern, so we can chop it up again into the 3 individual bytes that we want to encode. And this is where bit shifts and bitwise operators come in. So they happen. Here, what we want to do is shift them in such a way that the patterns don't overlap in the columns anymore. So the first one we leave alone. The second one we shift to the left by 6, which is sort of equivalent to pushing in zeros from the right. So you can also sort of see a binary number in this way as an array that you can pop elements off or push elements onto. Then the next one we shift by 12, and the final one by 18. And then we can use a bitwise OR to sort of squash them together. So that asks for every column, is there at least one 1 in this column? Now we have this 24-bit sequence, and we can use shifting to the right and the unsigned int8 encoder to encode the bytes that we have here. So a problem that you run into here is that you're now much more responsible for performance. And it really matters here. Sort of in contrast to JSON, where typically the payload is quite small, and also even with our parser, where most of those grammars are really designed to be easily parsable, and as long as you don't make or fall into particular pitfalls, you're going to be fine. Here, sort of the throughput matters. So if you want to encode a 2 megabyte file, you have to make sure that your encoder can handle that. So what you need to do is do a bunch of benchmarks. But the good thing is that you can totally do this afterwards. So even though all of these examples are quite technical, I think most of what is technical about it is coming up with how it works. And actually implementing this is reasonably easy. It's not that much harder than writing JSON decoders. So I think you can totally do that. So finally, I want to say something about why I like Bytes. I think a big part of it is sort of learning about various interesting things while writing, to my mind, meaningful code. So that means code that could end up in a package. So through using Bytes, because nothing exists yet in the ecosystem, because we don't allow JavaScript code, I get to play around with how does zip compression work and how do we decompress it? How do font files actually store the shapes of the curves? How does the base64 encoding work? How do we store 3D meshes efficiently and compactly? How do we decode them? So I think that has been a very useful experience to me. And so I think sort of why you should like Bytes is because they really enable a lot of new features. So we can send a lot more numerical data to the front end than we could before and sort of work with it efficiently. We can decode sound, we can decode images, we can decode archives, we can decode Word documents. And visualize them and find new ways to interact with this data. Also, if you consider like medical formats or something like that. Then I think it's a really nice and sort of safe way to interact with some fundamental computer science. So if you ever seen sort of bitwise operators before in some highly optimized piece of C code, they look very arcane, they look intimidating. But in Elm, they have really nice names. And it's clear from the name sort of what the order of the arguments is. And finally, I think there's a lot of low-hanging fruit in this area. And a lot of that fruit is sort of in small, self-contained problems. So I think there's a big opportunity here for people to come in and sort of create very small packages. And that is something I would really like to see is more people making that journey, sort of starting from scratch, designing an API, writing code, writing tests, writing benchmarks, all the way to publishing their first Elm package. I'm always available to talk about this kind of stuff, and thank you for your attention.